In this course, you've become much more facile with the manipulation of equations. And I'd like to demonstrate that to you with one last example. We're going to look at a gas inside, this time, a sealed container that doesn't leak, stopper. And we're going to have, again, two gases, neon and, let's say, argon. These are gases. PV equals nRT. But we have two different kinds of moles. The pressure, with total pressure times the volume, is equal to the total number of moles, with the total number of moles is the moles of neon plus the moles of argon, RT. And now at this point, I want to show how coming up with new concepts becomes very facile and very useful. And the concept we'll come up with is that of partial pressure. The partial pressure of neon is defined so that times volume, it equals the number of moles of neon times RT. So just take the number of moles of neon and you can get the partial pressure of neon. The partial pressure of argon times volume is equal to the number of moles of argon times RT. We can also take, because they are in the same flask, they have the same volume, the same temperature, we can divide the two. And we see that the pressure, partial pressure of the neon divided by the partial pressure of argon, that their ratio is just the ratio of the number of moles of neon to the number of moles of argon. So those are just algebraic manipulations. And how can this help us understand a language of understanding gas mixtures? Let's use some algebra here. We will distribute that parentheses, PV is equal to NE RT plus NAR RT. N and ERT is just this expression. And therefore we see that PV is equal to P and E of V. And NAR RT is just this expression. So this is equal to P AR of V. And we see that in this equation here, their volumes cancel. And so we end up with a very beautiful relationship that the total pressure, this is the total pressure, is just the sum of our defined partial pressures. And let's do a nice problem. So the total pressure is the sum of the partial pressures, and furthermore, the ratio of the partial pressures is the ratio of the moles. And let's see how we can use this language to understand systems of interest. And what we're going to look at is normal air. Normal air that's around us is at 1 atmosphere. And it is 78% N2, 21% O2, and 1%. What's the third most common molecule in air? Put it in chat if you know. It's 1% argon. Just comes in and out of us. It doesn't react with us. And we know that the number of moles is in the same ratio as the partial pressure. So the partial pressures are in the ratio of 78 to 21 to 1. So if the moles are in that ratio, here the partial pressures are in that ratio. We're just about done. The total pressure of air in the atmosphere is 1 atmosphere, and it's going to be the sum of the partial pressures, the partial pressure of N2, plus the partial pressure of O2, plus the partial pressure of argon. and they're in the ratio of 78 to 21 to 1, which means this is 0.78 atmospheres, and the partial pressure of O2 is 0.21 atmospheres, and the partial pressure of argon is 0.01 atmospheres. And so when you have a mixture, you can just take the partial pressures of the individual components, and they are in the ratio of the number of moles, and they add up to the total atmospheres. And this is the way that we normally think of gases. And I just gave this example to show how facile, how good we are now at just using equalities and relationships and coming up with concepts and understanding how things work.